Okay, this is the homework video for question 70. I'm on limited time tonight, so this is going to be a pretty short and sweet video. You've got this student who's shaking a string, and it's connected to a slightly larger or slightly heavier string connected to a slightly heavier string. The linear densities, which is mass over length, are mu, and then 2 mu, and then 4 mu. For the three strings, the student's shaking his hand up and down with a fixed frequency F, sending transverse waves down the string. In part A, what happens to the speed of the wave as it moves from the student to the wall? So remember, the only two things that can affect the speed of a wave on a string are the tension, the Ft, and the linear density, which is the mu. Remember, linear density is defined as mass per length, or mass over length. So the tension in all three strings must be the same since they're all connected together. It just depends on how tight the student's holding the strings. But the linear densities are changing. And in the notes, it says that the speed of the wave increases as tension increases, and it decreases as the linear density increases. So since the linear density is getting larger as the wave goes down the string, that means the speed must be getting smaller as it moves from the student to the wall. So it's a certain speed in that first string, then it gets a little bit less in that second string, then it gets less still in that third string. Now, for part B and C, speed is related to wavelength and frequency by that equation. V is equal to lambda, the wavelength, times f, the frequency. And the one thing you need to remember from the notes is that as a wave moves from one medium to another, the frequency is not going to change. The frequency is the one fixed thing as it's going from the lower linear mass density to the next lowest to the highest linear mass density. So in part B, the frequency is unchanged as it moves from the student to the wall. And then you can also use this equation to help answer part C, what happens to the wavelength. Since the wavelength, if you rearrange this equation, and this is the way it's given on the formula sheet, V over F, we just said in part A that the V is getting smaller as the wave goes down the string, the F is staying the same, so V is directly proportional to lambda, the wavelength, which means the wavelength is also getting smaller. In part D, the speed of the wave in the first string with the linear density mu is 20 meters per second, and it says the speed of a wave on a string is inversely proportional to the square, and actually I just realized that's a mistake in the problem. That should say the square root of the string's linear density. So V is equal to, doesn't really matter what the rest of this equation is, just know that it's inversely proportional, which means in the denominator, and inversely proportional to the square root of the linear density. So using proportional reasoning, if the linear density in the last string is 4 times as much as the first string, so I'll multiply that mu by a 4, how does that affect the V? Well, the 4 is under a square root sign, so it's in the denominator. So it's under square root sign, which makes it a 2 on the left side of the equation, and the fact that it's in the denominator means we have to put it in the denominator on the left side of the equation. So the speed is 1/2 as much, based on the fact that the linear density in the last string is 4 times as much. So since it was 20 meters per second in the first string, that means it's going to be 10 meters per second in the last string. Now, if you had answered this question with the mistake, I'll go ahead and give the answer that way as well. So what I wrote in the question, even though it's not the case, is that it's inversely proportional to the square of the linear density. So if you solved it this way, and you said the linear density was 4 times as much, which that 4 will get squared and is still in the denominator, then the velocity will be 1/16 as much in that final string. Okay, in part E, the student then begins shaking his hand up and down with a frequency 2f. So by doubling the frequency, how does that affect the speed and the wavelength? Well, remember what we said earlier. The only two things that will affect the speed of a wave on a string are the tension and the linear density. Nothing else will change the speed. Even though it looks like, according to this formula, that the speed will change if you double the frequency, people are inclined to say that the speed doubles also. Remember, this is the better way to put the formula, because it's showing that the wavelength is what changes when you double the frequency. The speed will stay the same because you have not changed the tension and you have not changed the linear density. So that's E1, and then E2. Since the speed stayed the same and the frequency doubled, that means to compensate, since these are inversely proportional, the wavelength would have to be 1/2 as much. So that would decrease because of this equation. And in part F, what happens to the wave when it reaches the hook on the wall? So this is talking about reflections of waves. Remember, there's something that happens when it reflects from a fixed point, and something that happens when it reflects from a free point on the wall that's free to slide up and down. This hook is fixed in place, so just consult your notes and see what happens to a wave when it, or if you remember it, just see what happens to a wave when it reflects off a point that is fixed in place. And that's your answer to part F.